You probably know that moving clocks tick slower compared to the ones that are at rest, or that clocks that are closer to a black hole tick slower compared to the ones that are far away. But there's something even more important. These are both wrong. I kid you not. This turns out to be one of the most misunderstood ideas in all of relativity. Clocks never tick slower, time never slows down. When I first read about this in a book called Exploring Black Holes, a highly suggested book on general relativity, I had the my whole life was a lie kind of moment. I mean, what do you mean this is wrong? Isn't this at the heart of relativity? And if time never really slows down, what exactly is time dilation? It felt like I was back to square one. Nothing made sense until now. After going through that book thoroughly, oh my God, I think I finally get it. I understand that this is a big misconception. I've had it for a long time as well. So by the end of this video, you and I will move away from these metaphors and we'll step by step rediscover from scratch, purely intuitively, how physicists actually think about time dilation. So if you're ready for this, let's begin. So where do we start? Well, let's talk to Archibald Wheeler, the co-author of that book, Exploring Black Holes. And if you don't know who that is, he's the person who coined the term black hole. So legendary guy. All right, Wheeler, why is it wrong to say a moving clock runs slower? Wheeler says because Einstein's relativity never said that. Wait, what? Yeah, instead it says you will measure a moving clock to run slower. And at this point, I'm disappointed. Isn't that the same thing, Wheeler? What's the difference? And Wheeler says, oh, it's a big difference. In fact, let me give you an example. You and your friend are moving side by side in a car. You glance over and see yourself overtaking her. So you measure her car to be slower. Does that mean that her car is slower? And I say, of course, that's how normal people talk. We don't say, I measure your car to be moving slower. We say your car is slower. And Wheeler says, okay, but what if both of your speedometers read exactly 100 miles an hour? In fact, what if she sees herself overtaking you and she measures your car to be going slower? Then what? Wheeler, what nonsense is this? You're saying both of our cars are going at 100 miles an hour and yet we both see ourselves overtaking the other person? How does that make any sense? Wheeler says, let's look from the top. If both of your cars were actually going exactly parallel to each other, yeah, then it doesn't make any sense. But what if your cars were having an angle? Now look, even though both of your cars are moving at exactly the same speed, from your perspective, you're overtaking her. You measure her car to be slower. But from her perspective, she's overtaking you. She measures your car to be slower. So look, Mohesh, right in front of your eyes. Just because you measure the other car to be slower doesn't mean it is slower. So what's going on over here? Well, both of you are judging the other person's motion from an angle. That's why you see the other person's car to be going slower, even though it's not. Your perspectives are tilted. Isn't that incredible? Wheeler says your friend and you measuring the other person's clock to be slower are exactly like these two drivers. I mean, the situation is so incredibly analogous. So just like the car speedometer, both of your clocks are ticking at exactly the same rate. Time is passing at the same rate. Now in the car's example, you measured the other person to be slower because you're measuring each other's motion from an angle in 2D space. Similarly, here you're measuring each other's clock to be ticking slower because you are measuring the motion from an angle in 4-dimensional space-time. So if you want a full intuition of what's going on, just like before, we need a top view, a space-time top view. We need to draw a space-time diagram. So let's do that. So let's bring them together and draw a space-time graph. So over here, the horizontal represents the space and the vertical represents the time. Let's choose a reference frame in which they're both moving away from each other at exactly the same speed. It'll make things super analogous to our cars, okay? So here's what it will look like. Look, they're going away from each other at the same speed. This is called their world lines. And now look at how analogous the situation is with respect to the cars. Oh my God. Over here, the cars are moving at exactly the same speed through space. Here, both of us are going at the same speed through space-time. Here, both the cars have traveled exactly the same distance in space. So let's say 100 miles. Meaning if their odometers reading was 0 here, both of their odometers over here will be 100, right? Here, both of us have traveled exactly the same distance in space-time. Now, in space-time, this distance is called proper time. It's a measure of how much we have aged or how much our clocks, our personal clocks have ticked. So for example, we can say 3 years. Both of us have aged exactly by 3 years. So if both of our clocks were in sync over here and say it was 0, then here it would read 3 years. Our clocks are like the odometers over here. So look, clocks are ticking at the same rate, time passes at the same rate for everyone. So just like how here we are measuring each other's motion from an angle, and that's why we measure the other person's car to be going slower. Look, we are measuring each other's person's motion through an angle in 4D space-time. That's why we measure the other person's clock to be ticking slower. Even though clocks are ticking at a normal rate, time is passing normally. Now, this is already starting to blow my mind. I'm starting to get some beautiful intuition, but Wheeler, over here, I was able to draw my line of sights and then rotate to look at things from my perspective, and I could clearly see why I measure her to be behind me, and similarly why she measures me to be behind her. I could do that. Can we do the same thing over here? Is it possible? And Wheeler says, yeah, we can do that. We can draw line of sights and we can rotate and we can measure from each other's perspective, and this will be super clear. And I'm like, all right, Wheeler, let's do it. Let's get that intuition. Okay, so are you ready for it? All right, let's do this. Let's get rid of this. Let's draw a line of sights in space-time and let's rotate. Oh my God, wait, what the heck? What is this? Wheeler, I don't understand what's going on. Stop, what is this? And Wheeler says, oh, I forgot, Mahesh, you don't have intuition for space-time rotation, right? And I'm like, what the heck is a space-time rotation? Wheeler says, all right, Mahesh, let's take a step back. Let's come back to the cars over here. When we rotate, over here, we follow a circle, right? Why? Why does rotation over here follow a circular path? And I say, well, that's what rotation is. You know, rotation is circular, right? And Wheeler says, no, it's got something to do with the geometry. What do you mean? In normal space, the distance formula is given by the Pythagoras theorem, right? And we know that x and y displacements are arbitrary. They depend upon your graphs and how your axes are tilted. But the value of this distance is absolute. It's an invariant. It doesn't matter who looks at it. Everybody agrees that this is, for example, 100 miles. And so look, this is a constant. And so we have x squared plus y squared is a constant, which is a circle. That's why the rotations are circular. In fact, think of it this way. If my axis tilts such that x value increases, then the y value has to decrease so that the sum stays a constant. And that's why if x value increases, the y value decreases. Similarly, if the x value increases here, the y value must decrease in such a way it traces a circle. That's why rotations are circular. Okay, that kind of makes sense. Now, what about in space-time? The distance formula in space-time is given very analogous to Pythagoras theorem, but with a minus sign. And if you're wondering where that minus sign comes from, we'll talk about that in great detail in our previous video. I'm not trying to fish for views over here, but I want to tell you that this doesn't come just like that. It can be rediscovered from scratch, step by step. And I've done that in a previous video. So if you need the intuition for that, feel free to check that out. But for the purpose of this video, we're just going to borrow that the distance formula in space-time, very similar to Pythagoras, but with a minus sign. So Wheeler says, Mahesh, look, just like over here, the t value and the x value are arbitrary. They depend upon reference frame, how your axes are tilted. But the value of this distance, proper time, that's an invariant. So this time, our equation becomes t squared minus x squared is a constant. What is that equation? That is a graph of a hyperbola, a rectangular hyperbola. Again, to get some more intuition, think of it this way. This time, if x value increases, the t value should also increase so that the difference stays a constant. So if the x value increases, the t value increases, and if the x value increases here, the t value increases. And so we now get a hyperbola. So in space-time, the rotation must follow the tip of a hyperbola. That is the difference between rotations in normal space and rotations in space-time. And this is super non-intuitive to begin with, but once we get some practice with this, oh boy, everything is gonna fall in place, okay? But Wheeler, wait a second, I have a question. You can draw lots of hyperboles, right? Hyperbole. Which hyperbola should we draw over here? Wheeler says, excellent question. Remember that the world lines can have a maximum angle of 45 degrees. This represents the speed of light. We're assuming the speed of light is 1, giving you an angle of 45 degrees. Since you cannot go beyond the speed of light, these hyperbolae cannot go beyond the 45 degree lines. In other words, these 45 degree lines form the asymptotes or tangents to the hyperbolae at infinity. And so only the hyperbolae which have these 45 degree asymptotes are the ones that we draw over here. And so look, our distance formula in spacetime represents a family of hyperbolae with vertex at the origin. And similarly, the distance formula in space represents a family of circles with the center at the origin. Look at how analogous the situation is. Oh my God. If you were to draw lines from here all the way to this particular circle, they all have the same length because they're all the radii. So in this particular case, we can say they all are 100 miles, and therefore this circle represents a 100 miles circle, right? The same thing applies over here. All the lines drawn from this point onto the hyperbolae are of the same length in space-time. And I say, Wheeler, but they don't look the same length. They look different. And Wheeler says that's the whole point. This geometry is non-Euclidean. You can't draw non-Euclidean geometry on paper or on screen. It gets distorted. That is what makes it super non-intuitive, but at the same time, super duper interesting. But the analogy is so amazing that I can use this to derive insights. I can now say all these lines, even though they look different, they must all have the same length. And when I say length, I'm talking about proper time. So they all, for example, in this case, have 3 years. These lines are all 3 years long. And so we can say this is the hyperbola of 3 years. And so therefore, just like how while rotating over here, we follow the tip of a circle because they all represent 100 miles. While rotating, we should rotate along the hyperbola because they all represent 3 years. Does that make sense? Okay, so are you ready for the rotations now? Let's do it slowly. Here goes. Just like how I have now gone into the perspective of the red car, I am now looking at things from my reference frame. Similarly, we can go back and go into her reference frame. Similarly, we have gone into her reference frame over here. Isn't that amazing? So we have gotten the first thing down. We now understand how to do rotations. But now comes the second thing, line of sight. How do you draw line of sight? Well, look, the line of sight is drawn. Let's get clear all of those things. The line of sight is drawn tangent to the circle. Similarly, over here, we're going to draw a line of sight tangent to the hyperbola. But Wheeler, I have a question. Wait a second. Over here, I know what line of sight means in space. But what is the meaning of line of sight in space-time? Wheeler says, great question. Let's go back to the analogy. So if I were to look at my line of sight, for example, what this represents is that all the stuff that is in front of it, that is something that I'm yet to cross, right? I'm continuously moving, so I'm yet to cross them. So in some sense, they lie ahead, they lie in my future. And all the stuff behind, well, I've already crossed them. So they lie behind me, they lie in my past. And all the stuff that is right along this line of sight, they are currently, I'm passing them right now. So that represents my present or simultaneity. Wait, why is it called simultaneity? Well, because all the stuff that is there right now, for example, if there are 2 barrels right now, they're in my present because I'm currently crossing them and I'm crossing them at the same time, simultaneously. So the line of sight really represents the line of simultaneity. it tells, from my perspective, what is future, what is past, and what is simultaneous. Now, guess what? The same thing applies over here. All the events, remember this is space-time, so every single point is an event. So all the events above this line represents my future. All the events below represents my past, and all the events along this line represents my simultaneity. So if there are two supernovae explosions over here, in my perspective, they are simultaneous. Now, I may not see them simultaneously because this one is closer, so its light reaches me before the light from here. But if I were to do all the calculations, I would eventually conclude, hey, these two happen simultaneously in my frame. But remember, her axis is tilted with respect to mine, so her definition of future, past, and simultaneity is different. And therefore, for example, she will disagree that the two barrels are simultaneous. She will say she passed through this barrel first, then she passed through this barrel. And now imagine how weird their conversation would be if they couldn't perceive this angle. They might be thinking they're moving parallelly. And so one person says, hey, I passed both the barrels at the same time. The other person says, I passed one barrel first and then the other one. And they're wondering, how is that possible? Relativity of simultaneity. But we understand from the top view, hey, come on, folks. This whole simultaneity business is relative. What's important is that these two barrels are there on space. Now, whether they are simultaneous or not depends on your tilt, depends on the direction in which you're moving, obviously, right? The same thing applies over here. My friend's simultaneity axis is tilted. So her definition of future, past, and what's simultaneous is different. In fact, look, she says the two supernovae explosions are not simultaneous. This happened first. It's already in her past. And now this is happening. And so we disagree on what's simultaneous and what's not. And we make a big deal out of it, thinking that, oh my God, relativity of simultaneity, oh, non-intuitive. But it's only non-intuitive if you think in terms of space and time separately. If you were to look at the top view, it makes perfect sense. The two supernovae exist on space-time. That's a fact. Now, whether you call them simultaneous or not depends upon the angle in which you're moving in space-time, and based on that, how your simultaneity lines are tilted. I don't know about you, but doesn't this make so much sense? Oh my God. So, long story short, the line of sight really represents the line of simultaneity. And Wheeler says, Mahesh, so now you have the full picture, you have the full context. Can you look at this diagram and see what each one measures the other clock is doing? And I'm like, yeah, we can. I mean, look at this. From my perspective, right now at my present, it's 3 years. But my line of simultaneity cuts through her past. And that's why when I measure her clock, I will say it's less than 3 years, maybe about 2 years. So you can see right in front of your eyes, the reason for that is not because her clock is ticking slower. The reason is because my axis of simultaneity is tilted. My present cuts through her past. It is so analogous, right? And the same thing applies to her as well. From her perspective, look, her simultaneity cuts through my past, and so she measures my clock to be behind her. It's all about our tilts in simultaneity. That explains it all. So now let's do a rotation and see, from my perspective, her clock is behind. And from her perspective, my clock is behind. I am getting goosebumps over here. So now Wheeler asks, Mahesh, let's go back to your original statement. Saying a moving clock runs slower is equivalent to saying a car's odometer, measured from an angle, runs slower. Do you agree with this? No, I don't agree with this. Sure, when you measure a car's motion from an angle, you will measure it to be slower. But saying that its odometer is running slow, that's absolutely wrong. No, you measure it to be slower because it's geometry. You're measuring it from an angle. But saying its odometer is running slower with respect to me, or its wheels are spinning slower with respect, no, none of that is happening. This is wrong. The same idea holds here, says Wheeler. When an object is moving in space, what's really happening is that you're measuring its motion from an angle in 4D spacetime. And because our simultaneities are tilted, we measure the other person's clock behind us. But it would be wrong to say that their clocks are running slower. Absolutely wrong. And I hope you agree now the same thing applies to gravity as well. Black holes, for example, don't slow down time or make clocks run slower. No, all it does is it curves space-time, and that affects what we think is simultaneous close to it. At the end of the day, it's a comment on how simultaneity is changing. It's a comment on geometry. That's why these are useful metaphors for beginners who don't want to think about hyperbolic geometry, but man, this is so wrong. It causes so much misconceptions. We are so much better off with this picture. It is the most accurate way to think about time dilations. It's how physicists actually think about it. And once we get comfortable with hyperbolic geometry, it starts making intuitive sense. This is the way. This is the way. By the way, now that we're thinking about relativity geometrically and not as time slowing down, all kinds of time-related misconceptions go away. For example, a common misconception is that, hey, if you travel at very high speeds, you age slower, you live longer. Wrong. Time never slows down, clocks never tick slower. If you go close to a black hole, you age slower, you will live longer. Wrong. Time never slows down, clocks never tick slower. As you enter the black hole, the rest of the universe speeds up, and so you see the entire future history of the universe behind you. Wrong. Clocks never tick slower or faster, time never slows down or speeds up. All of those things go away. And the most notorious paradox, the twins paradox, goes away as well. I mean, earlier we would think that, hey, if my twin were to go very far away and then come back, I am at rest, and since moving clocks run slower, her clock must be running slower. She must be aging slower, and so she must be younger. But the same thing applies from her perspective. From her perspective, she is at rest, and the rest of the universe moved away and then came back. So it must be the rest of the universe, their clock must have been, slower, and therefore I am the one who's younger. Paradox. But now it goes away because we know this statement itself is wrong. Clocks never tick slower, time never slows down. Boom! Twins paradox goes away. But wait, I have a problem. If time never ticks slower, clocks never slow down, then we would predict both of them to be of the same age, right? But we know that's wrong. Relativity predicts that she would be younger. How does that make any sense, Wheeler? So Wheeler, if time never slows down, it's just a measurement artifact of simultaneity axis tilting, how can people age differently? And Wheeler says, well, Mahesh, it's kind of like how you can spend the same amount of time trying to learn something and yet get much deeper intuition if you use Brilliant, the sponsor of this video. I love Brilliant because you can start becoming a better problem solver for free. Just like my videos, it helps you rediscover concepts by making you interact, reason, get challenged, all to help you build deep intuition. For example, look at the new course on coordinate transformations, something we do a lot in relativity. It immediately starts by making you move points using your mouse. You then use that intuition to translate using coordinates, and before you know it, you will be discovering all sorts of translations, rotations, reflections, stretchings, and whatnot. They now have a huge range of content in math, science, programming, data, or even AI for that matter. It's also personalized, giving you deliberate practice and helping you review and advance at the right pace. At the end of the day, it helps you build a regular learning habit. It's definitely a great habit to add to your New Year's resolution. Most importantly, you can get started for free. Just go to brilliant.org/FloatHeadPhysics and you can start using Brilliant for free for a full 30 days. You can also scan the QR code over here. And for my viewers, which is you, also get a 20% off on the annual premium subscription. The link is also in the description. All right, happy learning. Back to the video. So Wheeler, how can people age differently if time passes at the same rate for everyone? And Wheeler says, great question. Let's go back to the car analogy. And I love it. This car analogy has all the answers. Okay. So we have two cars moving at the same speed. That's the point. Moving at the same speed, taking this path. What if they decide to meet up at some point, say over here? So the question is, if their odometer reading is 0 over here, then what will be their odometer reading when they pass through this point? Will they be the same or different? And I say that's a straightforward question. The blue car would have a higher odometer reading. It has traveled a longer distance. But Wheeler says, Mahesh, they're both traveling at the same speed. Their odometers are running at the same rate throughout the journey. Then why does one accumulate more odometer reading compared to the other? Because they take different paths. Exactly. If you take different paths from one location to another, you will accumulate different odometer readings, right? The same thing happens in space-time. If you go back to your twins, the twins case, then look, between two events of separating and then eventually meeting, they both take different paths through space-time. Just like over here, when you take different paths, you'll end up with different odometer readings. If you take different paths over here, you'll end up with different odometer. In other words, your proper time readings. Therefore, by taking different paths through space-time between two events, you can end up aging differently. Okay, that makes sense. All right. So now let's dig deeper. Wheeler asks, which of them would have a higher odometer reading, you said? I said this one, right? Why? Because this path is longer. How do you know that? Come on, this path, I can see it. No, the point is that over here, things might be intuitive, but over here, it's not. So you need to find a really elegant way to convince yourself that. Okay, here's how we can do that. I can draw a line over here because it's symmetric about this point and compare these two paths. If I draw a circle, because we live in a circular geometry over here, then I can immediately see that, hey, look, this path is longer than this path by this much amount because it sticks outside the circle. And similarly, I can say this path is longer than this path, so this total path is longer than this path, and therefore this path is longer. Boom. And now Wheeler says, Mahesh, perfect. Moment of truth. Can you apply the same thing over here and convince yourself of which path is longer and which is shorter? Instead of circle, you have to draw hyperbola. Great idea to pause the video, folks. Moment of truth. Please try. Okay. We divided this into two paths. We'll divide this into two paths as well and only focus between these two path lengths. And to do that, instead of drawing a circle centered here, we're going to draw a hyperbola centered over here. How do you draw a hyperbola? Well, first you draw your light cones because that, light paths, because 45 degrees, that will be your asymptotes. And then you draw a hyperbola and then we'll get rid of them because that's not necessary. Okay, so now we can look at this and we can say, hey, this path is shorter than this one by this much amount. Can you see? Because remember, all distances from this point to the hyperbola are equal, but this one is shorter. And therefore, this path is shorter than this one. And of course, the same logic applies over here. And as a result, look, the traveling twin took a shorter path. And therefore, she accumulated less distance, which is less proper time. Therefore, she is younger. Even though clocks are ticking at the same rate, time is passing at the same rate, she took a shorter path through space-time between these two events. That's why she is younger. Oh my God, this is it. This is how you think about time dilation. And Wheeler says, now I know you have a question about her perspective. We'll get to that. But before we do this, we can now come up with a principle. See, over here, between any 2 points, if you take a straight line, that is the shortest path, right? If you take any bent path, that is longer. More bent, longer the path becomes. The same thing applies over here, but it's in reverse. The straight line between any two events, that path is the longest path. If you take a bent whirl line, that path becomes shorter. If you bend it even more, that path becomes even shorter. So over here, we can say straight paths is the shortest distance between two locations. What can we say here? Well, straight paths is the longest distance between two, not location, events. Why longest? because of the non-Euclidean. That's the weirdest part over here, the non-Euclidean geometry, the negative sign that we saw earlier in the Pythagoras theorem. But what exactly is a straight path over here? What is the definition of straight? Well, over here we can say something is straight if you're driving in such a way you don't have to turn your steering wheel. Then you know that you've taken a straight path. That's the best way to define straight over here. Over here, what is the definition of straight? When do we say a whirl line is straight? If there are no forces acting on you, if you're not accelerating, if you have an inertial path. So we can say inertial path will always accumulate what is distance, proper time. So inertial path will give you maximal proper time or maximal aging between two events. And so the reason why the Earth twin is aging more is because he took the inertial path from this event to this one, but the astronaut took a non-inertial path, a shorter path. So she aged less. But Wheeler, now let's come to the main argument. Her path is bent from my perspective. That's why she's taking a shorter path, appearing younger to me. But wait, can't I say from her perspective, she is traveling a straight whirl line and it's my path that is bent? Can't I do that? And so I would end up being younger. The paradox remains. Wheeler says, okay, let's come back over here. From the red card's perspective, it took a straight path, but the blue one took a longer bent path. So can I now say from the blue card's perspective, it took a straight path and the red one took a longer path? No, you can't say that. No, I mean, it's an objective fact that the blue card took a longer path, right? Like, it doesn't depend upon your reference frames. The blue car has traveled more distance. That's it. That's an objective fact. This doesn't work. This doesn't work. And so Wheeler says, in the same way, this doesn't work. The reason why it doesn't work is because those transformations are not allowed. You can't rotate like that. The only rotation that's allowed over here is circular. So if you do a circular rotation, look, whatever you do, you can't make that bent path straight. The fact that this path is bent is an objective fact. So it doesn't matter how you rotate, you will always end up with the same fact that this path is longer. The same thing applies over here. You can't do any rotations. You are only allowed to do hyperbolic rotations over here. And when you do those hyperbolic rotations, you will always find that it's this path that is bent. And therefore, and you'll always find that the red one is traveling straight, inertial path. So it will always have maximal aging and the traveling twin would be younger. Okay, Wheeler, but wait. If I were to put a camera on the blue car and follow it, I could in principle say that it is taking a straight path and the rest of the world is the one that's turning, right? I could say that, right? Yeah, you can do it, but the outcome will not change. Why not? I mean, I know it doesn't, but like, why not? Let me see it. It says, let's do it. So let's look at an animation, okay? So from the red card's perspective, this is how the animation looks like. Okay, now let's focus on the blue car and let's see what the animation looks like from here. Okay, since the camera is there on the blue, we'll assume that the blue car did not turn, it's the rest of the world that turned. So, boom. This is what it looks like. And look, when the rest of the world turns, this car teleports from here to here. Of course, it's not really teleporting, it's just that the rest of the world turned. And so now the animation continues. And sure, by doing some hacks and mid rotations, you can make this whirl line straight. But then this whirl line gets cut and the outcome is the same. This path is longer and this path is shorter. That fact does not change whatever you do. The same thing happens in spacetime. You can try to make this whirl line straight by doing mid-level rotations and stitching them together like we did in this case. But then this will get broken and whatever you do, the fact remains that this whirl line will be shorter than this one. It's an objective fact that the red car did not turn their steering wheel. It's an objective fact that the blue car turned their steering wheel. That does not depend on reference frames. Same is the case over here. It's an objective fact that I took a straight whirl line. I took an inertial path and she's the one who accelerated over here. That fact cannot go away by doing any kind of transformations. And that's how your paradox gets resolved. Okay, the final question we could be having is, all of this is in flat spacetime. But what if we go to curved spacetime? Wheeler, it looks like things are going to get super complicated, right? And Wheeler says, actually, no. Come back to the cars over here. Okay. If this was not a flat space, but it was, say, curved, there was a hill over here or something like that, the principle still applies. The person who does not turn their steering wheel ends up taking the shortest path, and the one who does turn the steering wheel takes a longer path. That principle works even when there is curvature, right? The only thing that we need to modify is we need to be careful about the word straight. Straight doesn't make any sense anymore because your world itself is curved, but that's okay. Our definition of straight is that your steering wheel does not turn. As long as you have a path in which the steering wheel does not turn between two locations, that is the shortest path. We call this paths geodesics. So we say the geodesics is the shortest distance between two locations, even in curved space. Guess what? The same thing applies over here. Even if there was curvature over here, the same thing would apply. Inertial paths, it need not look straight, it might get distorted, but the path that is inertial, the path in which there is no forces acting on it, will end up having maximal aging between the two events. So you can see why physicists love this way of thinking, because it doesn't matter whether you're in flat space-time or curved space-time, this principle applies. You don't have to think about gravitational time dilation, inertial kinematic time dilation. This is a single principle that applies in general. But there's a second effect that, again, we can see from here. If you take the distance between 2 points on a flat space, notice what happens to the distance when we add curvature. It becomes longer. Even though the car has not turned its steering wheel, it's going straight, the path length becomes longer because of the curvature, right? So your odometer will end up accumulating more distance when it's passing on a curved space. The same thing applies over here, except it'll be the opposite. If your world line passes through a strongly curved space-time area, your odometer will accumulate less proper time. Again, why less? Because of the negative sign. Which means, let's say that there was a black hole somewhere over here. Let's say the black hole is far away from the Earth, so it doesn't affect me much. But the traveling twin comes very close to the black hole and then goes away. What happens now? Well, first of all, we know that this traveling twin has taken a non-inertial path to begin with, so that's a shorter path to begin with. But now that she goes close to a curved space-time, curvature reduces her proper time. It doesn't increase, it's the exact opposite. Just like curvature increases the distance, the curvature over here reduces the proper time even further. And therefore, now when she comes back even younger than in the flat space-time case. So that's why when you travel close to a black hole and come back, you end up becoming super young, not because your clock ticks slower or anything like that, but the effect of curvature is that you end up accumulating even smaller proper time along that path. And again, if you ever get confused, come back over here. Just like how when a space gets curved, it adds more distance. Similarly, when space-time gets curved, it reduces your proper time for the world lines that are close by. That's basically how it happens. So, putting it all together, how do you think about time dilation in the most accurate way without resorting to metaphors like time slowing down or clock ticking slower? Well, first start with the familiar space. If you want to reach some location ahead of you, you can take a straight path that is the shortest distance, or you can take any other bent path, curved paths, which will give you longer distance, right? Similarly, if you want to reach a future event in space-time, an event could be something like being on Earth 1 revolution later, okay? You can take different paths. If you don't do anything, just sit quietly, take an inertial path to that event, you will age the maximum. And that happens to be about a year. Since most of us take an inertial path, most of us will end up aging by a year when one revolution happens. But relativity teaches us you don't have to take that path. You can take non-inertial paths like that of the traveling twin over here. You can go very far away and accelerate and bend your world lines, all by going close to a region where the spacetime is really curved, like a black hole or a neutron star. Both of this will shorten your spacetime path, and it'll allow you to reach that future event quicker. That's what relativity teaches us. You can reach those future events quicker. And so, for example, you can reach that future event, say maybe in not 1 year, but maybe in just 3 hours of your personal time. And when that happens, you would have aged only by 3 hours, but the rest of them who took inertial paths would have aged by a year. You end up younger than them. Not because your time was ticking slower, or not because you are aging different at a different rate. None of that. But because you took a shorter path through space-time to reach the future event, and all those other people took a longer inertial path. That's how you think about time dilation. I'll see you.